Hello and welcome to Team Starlight of Queen Mary University of London's preliminary design report for the Satellite Design Competition 2025. This year we are a team of 13. In addition to students from engineering backgrounds, we have pushed to include students from computer science too for the software aspect of the satellite. Our internal team structure consists of payload, power, structure, attitude and orbital controls and software teams. We've combined the software from each of the different systems into one team this year to streamline the process of developing the software. Additionally, we have a systems engineer who coordinates the interfacing between teams and ensures the entire design is within constraints. Using what we learned from last year, we project that the total cost of our satellite this year should be under £400 for the components, materials, and machining. We have already begun acquiring components and we intend to use many of the components of the previous year's satellite again in this year. Our money primarily comes from the Student Union Society Development Fund, our University Schools Fund, memberships, and the QMSEDS match funding, although these funds will be split between our satellite, rover, and rocketry teams. We will also be continuing our relationship with sponsors from last year and finding new ones as a way of supplementing the budget.
To mitigate organizational risk, team policies are developed. These include: the university deadline are not valid excuses for missing internal deadlines, as these can be prepared for early on. As the team is oversubscribed, we are operating on a 3-strike policy, because missing team deadlines places pressure on fellow teammates. All internal deadlines are also shifted earlier by 1 week. Miscommunication is to be mitigated by having the systems engineer communicate and decide on any important overall design choices.
This is our Gantt chart. We're using it to help manage team progress throughout the year. We've time blocked for different processes such as manufacturing and research, and then added the submission deadlines for the competitions on there with internal deadlines of a week before to allow for any unexpected disruptions or increased workload due to exams and deadlines for the team.
Now let's hand over to the individual teams to explain how we are designing our satellite for rendezvous and proximity operations.
Now let's have a look at our payload design. Our payload consists of 3 main elements to fulfill the mission task, and these include an onboard computer, a camera, and a docking system. For the onboard computer, we did trade-off analysis between a few, especially with the ESP32, which we had selected for last year's competition, so it was familiar to the team. It has a low price and low power consumption, but doesn't have the best performance. Therefore, we selected the Raspberry Pi Zero, which has improved clock speed for onboard image processing compared to the ESP32. It has 40 GPIO pins, which are essential for driving motors, and it has a good power consumption average. For the camera selection, we looked at an OV5624. Again, we used this in last year's competition, so it's already owned by the team, and it's a good camera with an SPI interface which is compatible with both boards. It has good resolution, at least sufficient for reading fiducial markers. However, with our new budget, we decided to go with the Raspberry Pi Camera 3, which has better resolution and is compatible with the Raspberry Pi onboard computer that we decided to go with. However, it does require an adapter. Finally, for our docking system, we selected permanent neodymium magnets, as they do not require power like electromagnets. They have the same configuration as on the Chaser satellite and are set in 70 by 70 millimeters square. We also selected a Hall effect sensor, which will be able to send docking confirmation message to the ground station. So it will measure baseline magnetic field without docking, and then we select a threshold for when docked. And it's cheap at ATP per unit.
The main components in the software architecture of the satellite are the 2 separate systems, a ground system and a satellite system. Looking at the UI, its purpose is to simplify the operation of the satellite significantly and make it more intuitive by abstracting away a large amount of the complexity. The satellite API sends commands to and receives gyro data from the ALCS, meaning ALCS functions as both input and output source in this case, whereas the ground API only receives data from each component in the satellite, meaning that EPS, AOCS, and payload function as input sources. A design with two separate APIs was selected as this enables a synchronous operation where tasks can be done independently by each system. For example, the satellite system can control the orientation of the satellite, while the ground system downstreams telemetry. This is beneficial as if this wasn't the case, the satellite would be slow to react to correcting its orientation because it may be trying to perform another task at the same time. After the satellite is activated, the satellite will perform a series of health and status checks to ensure the integrity of the satellite components and software is not compromised. After this is performed, the payload will begin sending data to the ground API, which will attempt to find a fiducial marker. If it cannot be found in the image seen by the payload, the ground system will communicate this to the satellite system, instructing it to enter a search mode where the satellite will rotate slowly. The satellite will continue to rotate while every frame from the payload camera is checked. Once the fiducial marker is located, the rotation of the satellite will be stopped. The ground system will then begin sending data about the angle of the marker relative to the satellite system, where instructions will be sent to the ALCS. This data will then be used to more accurately line up the satellite with docking.
Now that the satellite's general functions have been covered, I would like to focus on its image processing capabilities. The satellite is designed to operate autonomously, performing onboard processing based on the command it receives. Its primary focus is on image processing tasks aligned to its specific mission phases. In Phase 1, there is no image processing, while in Phase 2, the satellite captures images of its surroundings to detect number cards along with the digits on them. We plan to use machine learning model trained on publicly available datasets for this task. This ensures efficient and reliable detection capabilities within the constraints of the onboard resources. A key feature of this phase is the integration of a user interface, which will display the detected card images and would also provide an override functionality, allowing the operator to manually correct or validate the detections made by the satellite, ensuring a higher accuracy and adaptability. In the last phase, Phase 3, the goal shifts to detecting the position using fiducial markers. The provided marker would be a Euroko marker, which enables a satellite to determine 6 degrees of freedom, which includes the position and orientation, reliably. This capability is critical to achieve the objectives of Phase 3 as it works in conjunction with the AOCS to support precise maneuvering and task execution. Through these phases, the satellite demonstrates robust autonomy while balancing onboard intelligence and operator oversight, ensuring flexibility and reliability for mission success.
The Attitude and Orbital Control System is a particularly critical subsystem this year, as the SDC focuses on rendezvous and proximity operations. Missions such as the Astroscale Address-J mission, which maneuvered to within 15 meters of a piece of large space debris, highlight the need for highly precise attitude determination and control. The testing phases within the SDC are designed to replicate similar operational challenges. Each phase defines specific objectives that serve as benchmarks for success. There is the first phase, which is the statement of health. Phase 2 is pointing and performance and stabilization, and Phase 3 is split into 3 sections: mid-range rendezvous, proximity operations, and the final approach. These objectives inform the development of functional, performance, and design requirements, as well as constraints, guiding the design, assembly, integration, and testing processes for the AOCS. Detailed requirements are provided in the AOCS section of the appendix.
The AOCS software will be responsible for orientating our CubeSat to face the target CubeSat. We will output precise voltage values based on the AOCS hardware to generate the required angular velocity for the CubeSat to maneuver at a speed that allows us to complete the task in the designated time. Furthermore, the AOCS software will create the PID controller and calculate the PID parameters to ensure as our angular position gets closer, the CubeSat will slow down and stop exactly in front of the target CubeSat. To obtain the PID parameters, we'll use techniques such as Ziegler-Nichols method, as well as MATLAB's control system designer. This will be accompanied by experimental testing to account for any simulation errors. The gyroscope output will be used to determine our angular proximity and fed back to the system to continuously monitor our angular acceleration, speed, and position.
For actuation, we have considered a few different methods, including a hard disk drive, a brushless DC motor, or using a ferrofluid in a machine tube. As the highest ranking in the decision matrix, a hard disk drive, specifically the Seagate Savia 10000, will be used as it will provide us with the most optimal torque, weight, and size for our application. HDDs are also the cheapest in comparison to all of our off-the-shelf options and fairly reliable as they remain effective after a significant amount of shock is applied. The key differences this year are the 3D printing, a custom-made spindle, making it much lighter, and attaching more than one disc on our flywheel. This will allow for the area moment of inertia to spread out further to the edges of the disc, and physical tests are to be conducted since HDDs are cheap and they can be recycled.
The MPU 9250 is rated the highest in the decision matrix based on size, cost, weight, reliability, and effectiveness matrix. Multiple integrated sensors enable precise attitude determination with minimal hardware complexity. Low drift performance ensures that extended orbital operations occur without frequent recalibration. Dedicated onboard processor handles sensor fusion, freeing main controller from the other AOCS tasks, and it is a cost-effective solution with comprehensive software library support for rapid AOCS implementation.
Simulations have been conducted to support the design of the attitude and orbital control systems. Built within MATLAB, these simulations leverage visualization techniques to effectively communicate findings to the wider team. Although not fully accurate, these simulations offer valuable insights into general trends, supporting informed decision-making prior to physical testing and manufacturing. This approach reduces reliance on iterative cycles during the design and AIT processes, leading to significant cost savings. The D-tumbling simulation on the left provides a foundational tool for tuning the PID controller and testing alternative control strategies and flywheel options prior to physical integration. The actuator positioning simulation on the right provides insight into the optimal actuator mounting location so the torque transfer to the satellite can be maximized. However, incorrect positioning may introduce wobble, which can be mitigated through the close collaboration with the structural team and careful consideration of the CubeSat center of mass. Simulation outputs, as outlined in the appendix, have identified the correct positioning of the actuator at the bottom of the CubeSat. These simulations are being used in conjunction with physical testing to validate results and refine the approach. This approach builds on lessons learned from previous iterations, ensuring continuous improvements.
For the electrical and power systems, the battery cell selection primarily included the cell chemistry and the cell shape. Firstly, a comparison between lithium-ion, nickel metal hydride, solid-state and nickel-cadmium cells was conducted. This revealed that lithium-ion was unanimously the best cell chemistry option to go for, mainly due to its high energy density, which ensures efficient packaging within the 3-unit space, high efficiency and low maintenance due to advantages such as little to none voltage depression. Secondly, a comparison between cylindrical, prismatic, and pouch cell shapes was conducted, and this revealed that cylindrical cells were top choice due to their inherent resistance to mechanical stresses, wide commercial use, and high power output due to increased cell connections. Also, mounting cylindrical cells is much more convenient and simplistic compared to something, for example, like creating a casing for pouch cells. Further information on these selections is included in the appendix. Ultimately, the Sony Murata VTC6 lithium-ion battery cells was chosen for these reasons, along with its minimal degradation with 66.6% discharge capacity after 400 charge-discharge cycles, and this ensures prolonged longevity for the duration of the satellite's operation. The cells also have sufficient operating temperature ranges in accordance to the rules, and it also has high electrical output.
Our BMS system will be the BMS2 SBA. It is a basic 2S lithium-ion battery BMS designed to protect a 2-cell battery pack from overcharging, over-discharge, overcurrent, and short circuits. The battery management system will be utilized mainly for safety precautions to optimally and safely manage the flow of energy. For example, unnecessarily high discharge rates can be controlled by the BMS to prevent overheating, which ensures safety and greater efficiency. A major component of the BMS is the input of various parameters such as voltage, current, temperature, and state of charge of individual cells. This allows the BMS to determine the appropriate electrical output for sufficient power and battery health monitoring. We conducted research into various BMS systems, and the BMS2 SBA was found to be the right one due to simplicity, budget, and compactness due to size constraints. We also plan to build upon issues we recognized in the previous year, which involves high back current that can be detected with our BMS system, with diodes connected in the circuit to prevent and inform the onboard computer of any issues.
The INA219 sensor interface is a high-side bidirectional current and power monitoring integrated circuit. It is to be used in the CubeSat to measure current, voltage, and power consumption with high precision for the microcontroller, power source, and embedded systems. It has a low operational power consumption, and its bidirectional current sensing is useful during charging and discharging cycles of the cells. The next steps for the power team include refining and locking down on power requirements from all subsystems, investigating mounting solutions for battery to conserve space and ensure batteries can be dischargeable as stated in the specification, wiring and connections, cell form factor, choosing between the 18650 and the 21700, and the cell layout, which includes the series or parallel configuration. And lastly, electrical modeling of the BMS, the cells, and the INA219 sensors.
The material selection for the CubeSat involves comparing two aluminium alloys, 6082 and 5005, using CES EduPack software. These are two of the 5 alloys specified in the CubeSat design specification. The goal is to select materials with a low price to mass ratio to reduce costs while meeting performance requirements. Key properties considered include price per kg, yield strength, elongation, corrosion resistance, and durability. The comparison of these materials can be seen in the table in the bottom right. The graph in the top right shows the Young's modulus against price per kg, where the aim is to maximize the material index. Fabrication will involve purchasing screws, bolts, blocks, and sheet metal. Railings and rods will be cut from the blocks, while the sheet metal will be laser cut to form the main body panels. All fabrication processes will take place in the makerspace facilities.
The computer-aided design shows the simplified model from Team Starlight's previous year's design, on which will be built on. The design is in floors and can be adjusted depending on components such as the batteries, AOCS, and payload. The 4 corner rods act as stress concentrators, and the panels have threaded screw holes for the vibration table mounting. A 3D printed cable mount is also designed for the mystery room operation. A problem from the previous competition year showed that once assembled, there were difficulties fitting the satellite onto the vibrational table on the competition day. And so the team will be designing a CAD model of an external clamp that connects the CubeSat to the vibration table. Next steps include performing finite element analysis on the CAD model in order to simulate the vibration table and structural fairing test.
The next steps for the structure team include researching various alloys to ensure durable materials are chosen with consideration into reducing the amount of weight that is required. Furthermore, ensuring that suitable manufacturing processes are also taken into account during the project, and additionally, making sure that the parts that are designed are within a suitable time frame with correct determination of safety factors integrated, such as mechanical stresses at the beginning. Lastly, by collaborating with other teams, such as Payload and AOCS, to inquire with their tasks and how to integrate them within the structure team.
This report has detailed the hardware and design choices to achieve this year's mission for rendezvous and proximity operations of a satellite, in addition to an outline of operational procedures and the underlying software. I want to say a huge thank you to Team Starlight for the excellent work that has been put in so far, and I look forward to continuing this project. I also want to say thank you to our contact at QMSEDS, Mohammed Dira, who has been so helpful since this team started. Thank you for watching. The following are our references, and you can find supplementary information on the appendix document.